Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure today to welcome Nuvendu Jain from the UT Austin, who he tells me he actually has his PhD, maybe not in hand, but he's finished, turned it in, gotten it signed, so congratulations. It's always good to hear.
Thank you.
And he's going to talk to us about scalable monitoring today.
Well, thank you very much, Jim. And thank you very much for inviting me. So today I'm going to talk about PRISM, which is a scalable monitoring service we have designed and implemented for monitoring as well as managing large-scale distributed systems. This is a joint work with my colleagues at Texas, both my seniors and juniors. And the main motivation for this work arises from the fundamental challenge of how do you manage large-scale distributed systems. I want to make a quick disclaimer that even though I'm using an Apple and Keynote for this presentation, please do not hold it against me. Okay, so
We wouldn't be able to hire anybody.
okay, just give you some background. In April 2003 on Planet Lab, which is a distributed research testbed comprising of about 800 machines that are spread all over the world, a user login was compromised. And within a short period of time, half of these nodes were port scanning external sites. And as you would expect, it generated lots of complaints. So to prevent any further damage, Planet Lab had to be shut down temporarily. Now, of course, you can just blame it on the hackers and say, well, what can we do about it? But that would give them too much credit. Okay? Because in reality, it's not just the hackers, but there are several other reasons why our systems break, such as security vulnerabilities, hardware errors, operator mistakes, and I'm sure everyone in the audience here, as well as persons who are watching online, must have written a buggy application at some point in time. Okay? So the key problem here is that fundamentally, distributed systems are hard to manage. They are unreliable, they break in complex or even unexpected ways, and it's really hard to know what's going on in the system. Okay? So in order to manage these systems, what we need to do is to continuously monitor and check if there are any problems in our underlying systems. Okay? So I'm going to give you a 10,000 feet view of the problem. This is an oversimplified view, but it captures the necessary details. Okay? So here we want to monitor a large-scale distributed system comprising of, say, tens of thousands of nodes. At each of these nodes, there are several events happening at any point in time. So for example, an event could be a CPU load spike, or a bursty data arrival, or a memory bug or memory leak, because our operating systems aren't perfect. Right? So our aim here is to correlate these events together and find out what are these loud or the big events on a global scale. By loud events, I mean those events that when you look at each node individually, they may be small. But when you look at collectively across the entire network, they constitute a large volume. So for example, a network administrator here might be interested in which network links are heavily congested, okay? Or which web servers are heavily loaded. Or are there any buggy applications in my system that are consuming lots of resources? Okay? And even from a securities perspective, monitoring these systems is very important. Now, what makes this monitoring problem fundamentally hard are three key challenges. Our first challenge here is scalability. We need a monitoring solution that will scale both with respect to the number of nodes as well as the amount of data volume. Now, we can do centralized monitoring that will scale to hundreds of nodes, but what we need is a solution that will scale as these systems grow from tens of thousands, and the vision is to go towards millions of nodes. Okay? And similarly, the data volume here of these events could be massive. And there are applications today that generate hundreds of gigabytes of data each day, and we want to move it to even petabytes of data. Right? So we need scalability both with respect to the number of nodes as well as the amount of data volume. Second, we want to quickly respond to these events so as to detect any performance problems as well as find out any security threats. So you want to do monitoring in real time. And finally, we need a solution that is robust against both node and network failures and still gives us an accurate view of the system. Okay. So the bottom line here is that for monitoring these systems, we need to process large volumes of data spanning tens of thousands of these nodes, and we want to do it in real time. Now, of course, our actual problem is much harder because this picture is not drawn to scale. Okay. So to define the problem more broadly, our vision here is to develop a distributed monitoring framework that monitors the underlying system state, performs queries, and reacts to global events. And numerous applications which I've shown here have similar requirements, such as network monitoring, grid monitoring, storage management, sensor monitoring, and so on. And in the later part of this talk, I'm going to show you results from some of these applications that we have built and in some cases even deployed. Okay. So to realize this vision, we have designed and implemented PRISM. PRISM is a scalable monitoring service for managing large-scale distributed systems. Now, you might say, well, there's been a lot of work on monitoring. What's new here? Our key contribution and our key distinguishing factor here is to define precision as a new fundamental abstraction to enable scalable monitoring. So what do I mean by that? So specifically, our two big goals are to achieve high scalability and high performance, and to ensure correctness, that is, give a robust solution that can tolerate node and network failures. So by defining this new precision abstraction, we'll achieve these two goals. So specifically, to achieve scalability and high performance, we'll trade precision for performance. So think of you're getting an answer about the global state of the system. So giving you an exact answer will give you an approximate answer. Okay? But we will bound the degree of approximation. And further, we'll adapt these approximation bounds to handle large-scale dynamic workloads. However, in practice, failures can can cause the system to violate these approximation bounds. Therefore, to safeguard correctness, we'll quantify how accurate our results really are and how to improve this accuracy despite large system failures. Okay?
The accuracy known a priori or after the fact?
Yes, so I'm going to talk about this in the very next slide. So here are our two big goals. To achieve scalability and high performance and ensure accuracy or ensure correctness despite failures. So the way we are going to realize these two goals is to define precision in form of 3 dimensions: arithmetic, temporal, and network imprecision. Okay? So arithmetic imprecision, or AI, bounds the numerical error of a query result. Okay? So take a simple example. Instead of giving an exact answer with value 100, we'll give you an approximate answer. Say the global query in the system has a value, say 100 plus minus 10%, but the answer is guaranteed to have a maximum numerical error of at most 10%. Okay? Similarly, temporal imprecision, or TI, bounds the staleness of a query result. So for example, a query result has a maximum staleness of at most 30 seconds. That is, it reflects all events that have happened in the system until 30 seconds from right now. Okay? So although AI, or arithmetic imprecision, bounds the numerical error and TI bounds staleness, in practice, however, failures can cause the system to violate these guarantees. Okay? Therefore, we define a fundamentally new abstraction, network imprecision, that bounds this uncertainty or this ambiguity because of failures. So very simply, so think of this NI as a good or a bad flag. So when you get an answer, you get this flag, good or bad. So if the flag says good, then these AI and TI bounds are guaranteed to hold. Otherwise, they may not hold, and you cannot rely on the accuracy of the reported answer. Right? So for simplicity, I'm showing this as a flag, but in reality, it is a continuum as to what extent the system actually provides these guarantees to the end user. Yes, please.
Frequently in randomized algorithms and other areas of statistics, one makes theorems of the form, do the following, and your answer will be within 1 plus or minus delta of the true answer with probability greater than or equal to 1 minus epsilon. And I feel like network imprecision seems like epsilon, and arithmetic imprecision seems like delta. So when you say it's fundamentally new abstraction, I thought it sounds a lot like epsilon delta theorems of which I've seen a bunch.
So let me actually take it piecewise. So you're right essentially saying that the 1 minus delta abstraction is actually very equivalent to arithmetic imprecision. However, for network imprecision, essentially, yes, you can provide 1 minus epsilon guarantees, but there are essentially two cases that essentially I'm going to talk about. One is there are ways there's impossibility result that you actually cannot give any epsilon bounds, right? And there are cases where actually you can give those epsilon bounds, but they become very expensive, right? So essentially it is impossible at first and it is expensive at best, right? Essentially I'm going to talk about that notion. So in that perspective, so this new abstraction is actually fundamentally different. So I'm going to give in more details later. Okay. So these 3 dimensions nicely complement each other to enable our goal of scalable monitoring. Although the basic ideas of AI and TI are not new, okay, but we'll give new scalable implementations of these metrics and show that by carefully managing them, we can reduce the monitoring load by several orders of magnitude. And by using NI, we'll characterize how accurate our results really are and how to improve this accuracy by up to an order of magnitude. Now, the combination of these 3 dimensions is really powerful, and my theme throughout this talk is how this unified precision abstraction enables scalable monitoring. Get a question?
Is magnitude really enough to get you to 1 million machines with a petabyte of trace data each?
Are you talking about this?
I mean, 100x seems like that we're close to what you need.
So I'm also going to, so this is 100x is actually a relative term, right? So I'm going to also show you the absolute numbers in terms of as the system size increases, what is the absolute overhead, what is the performance measurements. Okay. So I've given you an overview and the basic motivation of the problem of scalable monitoring. Now I'll present the fundamental PRISM architecture and the key technologies we use to build PRISM. Then I'll describe how PRISM uses AI and TI to achieve scalability, and how by using NI will ensure accuracy of results and how to improve this accuracy despite failures. Okay. So let me first give you a quick overview of the PRISM architecture. The key idea in PRISM is to define precision as a new unified abstraction. And we define this precision abstraction in form of 3 dimensions. Arithmetic imprecision that bounds numerical error, temporal imprecision bounds staleness, and network imprecision bounds the uncertainty due to failures. Okay? So AI and TI allow us to achieve high scalability by trading precision for performance. And NI addresses the fundamental challenge of providing consistency guarantees despite failures. Okay? Now, each of these dimensions makes sense individually, but how they relate can be confusing. So let me walk you through an example. So suppose, very simply, we have a security monitoring application that wants to detect the number of port scan attempts on a given port across, say, all of the machines in this building, right? So this is, in particular, is the UDP port for the Microsoft IaaS web server. Okay. So the query here is that we want to detect the number of port scan attempts on this port, and our precision requirements are that give me the answer within at most 10% off from the true value, and the staleness should be at most 30 seconds. So Albert, does that answer your question? In terms of we are specifying the precision requirements a priori. There's also the work that the system actually gives us the best possible precision it can provide within a limited monitoring budget.
I guess I'm a little surprised you don't talk about the resources needed.
Yeah, so that's kind of a dual problem. I can go into that later. So this is our basic query. So given this query, the system returns back an answer saying the number of port scan attempts on this port across all the machines in this building is 500 per second, and characterize its accuracy using NI. Okay. So to understand this, suppose if our system had only AI, then we guarantee that the answer lies in this range, assuming no failures and negligible propagation delays. Okay. And we use AI to reduce our monitoring load by filtering updates as long as they lie in this range. So even if your answer becomes 451 or 549, you don't need to send any new updates, right? Because it still satisfies our guarantees. Okay. Now suppose if we had only TI, then we guarantee that the answer value is 500 and staleness is at most 30 seconds. That means this answer reflects all events that have happened 30 or more seconds ago. Younger events, that is between now and at most 30 seconds ago may or may not be reflected. But everything before 30 seconds is reflected here. Okay. And again, I'm here assuming that nodes in the network are reliable, and links have negligible propagation delays. And we use TI to reduce load by combining multiple updates together and then sending a single batched update. Right? So very simple idea. Now, when you combine AI and TI, then we guarantee that the answer lies in this range based on inputs that are no more than 30 seconds still. And by using this combination, we can further reduce the load by first combining multiple updates together and then sending a batched update only if it drives our answer out of this range. Okay, so essentially we're combining both numerical filtering due to AI as well as temporal batching to further reduce the monitoring overhead. Right? Now note that for both AI and TI, I said that I'm assuming nodes and network are reliable and links have small delays. And NI handles cases when these assumptions do not hold. So when my NI flag says good, then these AI and TI bounds are guaranteed to hold. Right? So this gives you absolute guarantees that the answer you're getting satisfies these accuracy bounds. However, when the NI flag says bad, then these bounds may not hold, and you cannot trust the accuracy of the reported answer. So it will be great if I can always give you this green light that yes, you can trust this answer, versus a red light that no, you cannot trust this answer. Right? However, in reality, our large-scale systems are never really 100% stable. So essentially, you will never get everything that your answer will actually always satisfy your bounds versus it never satisfies, right? So essentially, your answer always right in that range. So then NI actually provides this continuum metric as to what extent do these AI and TI bounds hold. So this is an overview of the overall PRISM architecture. Yes, please.
So earlier when you said something to Albert about this is the, I specified plus or minus 10% in my query. By the end of your slide, I thought that feels like it's the output. You're saying the output of the query is port 1434, 500 plus or minus 10%. Because otherwise I would never specify that. Right? I would never specify that as an input. So that record, record is an output?
So this and these two are part of the query.
Okay.
The system outputs the answer and characterizes its accuracy using.
Okay, got it. Great.
Right. Any other questions on that slide?
I might ask you about how it works.
Okay. Yes.
It may be simpler to say good or bad, but probably you have confidence.
Yes. So essentially, that's exactly what I'm going to turn into. Right. So when I say good or bad, it's a flag basically. It's a 0-1 flag, right? So good means great, everything is perfect, but systems are never really 100% stable. So I'm going to give you a continuum as to what extent. Okay. So this is the overall architecture. I'm going to talk about the key technologies we use to build the system. So key abstraction we are going to use for building scalable monitoring is aggregation. Aggregation, very simply, is the ability to summarize information. Okay. We define this aggregation abstraction in form of an aggregation tree that spans all the nodes in the system. So in this particular example, I'm computing a sum aggregate of the inputs at the leaf nodes. We perform this in-network aggregation and get the global aggregate value of the inputs at the root. So that's our basic approach. We're going to use this aggregation trees to collect or aggregate the global stuff of the system. Right? So the natural question is, how do you build these trees in a distributed environment? Okay. So to build these trees, a key technology we're going to use is distributed hash table or DHTs. And certainly this audience doesn't need an introduction to DHTs. Well, very simply, DHT is a scalable data structure that has become recently popular in the systems community. And it provides important properties of scalability, self-organization, and robustness. Now, I'm not going to go into the details of these DHTs, but the key point, or the only point I want you to remember from this slide is we're going to use DHTs to build a random aggregation tree. And for load balancing, we are going to build multiple such trees. So for example, you can build one aggregation tree that keeps track of the traffic sent to a given destination. You can build another aggregation tree that keeps track of which are the most heavily loaded machines in the network, and yet another tree that keeps track of which nodes are storing which files. Right? So our basic approach is aggregation, and we are going to use this aggregation trees to collect the global state of the system. Right? So now let me take an example that ties all of this together. So recall my first motivating slide where essentially Planet Lab was being used to launch distributed denial of service attacks, right? So we formulate that problem in form of this query that find out the top 100 destination IPs that are receiving the highest traffic from all the Planet Lab nodes. There are about roughly 800 Planet Lab nodes right now, right? So to answer this query, so think of it as finding out the top 100 destination IPs means that if there's a likely an attack that is going on a victim site, then it should likely be in the top 100 destination IPs because we are looking at the aggregate volume of the outgoing traffic. Okay. So how do we compute this query? We're going to compute it in 2 steps. In the first step, we are going to compute the aggregate traffic sent to each destination IP from all nodes in the system. So in this aggregation tree, the physical nodes are at the leaves, and the internal nodes are simply what I call virtual nodes that are mapped to different physical nodes. Okay, so in the first step, we're going to compute for each destination IP the aggregate traffic sent to that destination from all the nodes in my system. Right? This is my first step. So for all the IP addresses, I'm going to compute this aggregate traffic. And in the second step, I'm going to compute a top 100 aggregation function. And again, doing this in network aggregation, I'll get the global top 100 list. Sure, go ahead.
You're going to take every single IP address that every Planet Lab node is sending data to and compute and create a separate aggregation tree on it?
It's okay, this is IPv4.
And therefore it's scalable. So
I'm gonna hit that point on the very nail. So actually, I'm going to reverse the question. So do you know how many IP addresses are there at any point in time?
Well, it's only IPv4, so
Yeah, but I mean it's.
yeah, yeah.
I mean, in practice.
In the world?
Yeah. So at any, if you take a snapshot, or take a guess.
How many IP addresses are live in the world?
Well, 100,000.
Oh, no, it's
on
much
a
more
tier
than
1 ISP, there could be like millions of /24s.
Yeah. So take a guess. So how many? If you take a snapshot.
I'd say 100 million.
I'd say a billion because there are that many Windows boxes. They're sending the WR.
Well, actually, it's not that. It's about 1 million roughly. So.
There's only 1 million live IP addresses.
So if you take a snapshot, so if at any point in time, if you take a snapshot of the traffic that is going outside collectively from all the Planet Lab nodes, the number of unique destination IPs
Wait, this is the Planet Lab is talking.
Yeah. So essentially.
Oh, okay, that wasn't the question we thought you asked.
Okay.
That's
So
why
this
we-
is
that's why we're off by 3 or 4.
right. So this is the destination IPs that are being contacted by these 800 Planet Lab nodes that are spread around the world.
Okay, I'm actually surprised it's that large for. Okay.
Well, actually, if you take a snapshot, actually it is.
All right, I believe you, but I'm surprised. All right.
Okay.
So there are a million such aggregation trees.
And in principle, yes, in principle, we're going to build a million trees, right? But now a key observation is that majority of these IP addresses receive very few updates, right? So remember, we are computing the top 100 list.
I agree.
Right? So when essentially majority of these IP addresses receive very few updates, and if you set your precision or your accuracy requirements to say, give me these flows within, say, 1% of my maximum flow value, right? I'm sorry?
How do you know that?
Google interview
Right. Right. So if you take the 1% of the maximum flow, which is say roughly about 3.5 megabits per second, right, then you can actually filter more than 99% of these destination IPs. Right. So which is important for scalability, that now you actually, in principle, although you need to compute all these millions of IP addresses, the aggregate values for those, but essentially by using a small amount of imprecision or small amount of error that you're willing to tolerate in your answer, you can actually filter out majority of this noise. And you would still get the top 100 list with that bounded accuracy.
So you're filtering out, I'm trying to understand where, because you don't know how much is being sent to a particular IP address until you construct the tree and run it up to the root.
Which is
you must be filtering at the leaves, right?
Well, not quite, but please go ahead, which I'm going to actually cover.
For you to tell,
Yes.
This is going to be part of your talk. I'm not going to
Yeah.
guess what it is.
Yes, I'm going to go in the very next couple of slides. Okay. So, so I'm going to use it as my running example throughout this talk. I'm going to keep coming back onto it. But yes, we're on the right track. Okay. So essentially, now I'm going to talk about how we use this arithmetic imprecision to achieve high scalability. So arithmetic imprecision, or AI, just a quick recall, bounds a numerical error of a query result. That is, instead of giving you an exact answer with value 100, we are giving you an approximate answer. It's 100 plus minus 10%, but the answer is guaranteed to have a maximum numerical error of at most 10%. Right? So when applications don't really need exact answers, AI allows us to reduce load by caching old values and filtering small changes from these values. Right? So even if my actual true answer becomes, say, 91 or 109, I don't need to send an update because it still meets my error guarantees. Right? The two key issues in implementing AI are the mechanism question of how do you take this 10% error and divide it among the nodes in the system, right, as you were pointing out, and the policy question of how do you do it optimally. Right? So I'm going to first show you a flexible mechanism in which you can take a total budget and divide it in any manner across nodes in the system. And I'm going to show you an adaptive algorithm that performs self-tuning of these budgets to minimize the monitoring load. Okay. So the way PRISM uses AI is by installing these filters at each node in an aggregation tree. So remember, we are aggregating the global state of the system using aggregation trees. Right? So, and each such filter, which is at each node in an aggregation tree, denotes a bounded range, low and high, such that the actual value lies in this range, and the width of this range is bounded by our error budget delta. Okay? So in this example, I'm setting these filter widths for a sum aggregate. Right? So now when you get a new update, we only need to send this update if it violates our filter. So for example, if you look at an update here with value 5, we don't need to send it because it already lies within our error guarantees. That is, the answer lies between 4 and 6. Right? So you can simply cull it or filter it. However, if you get an update that lies outside the range, then we need to update it to the parent and adjusting these filter widths along the way. Right? So the two key issues for AI are the mechanism question of how do you take the total budget delta and divide it among the nodes in the system. So given a total budget delta root, you essentially have the flexibility to divide in any manner. So for example, the root can keep some part of the budget for itself and divide the remaining among its children. Okay? And the children recursively do the same. They keep some part of their budget for themselves and divide the remaining among its children, and so on. So in this way, you have tremendous flexibility to divide a total budget in any manner across the nodes. Right? Now, an intuitive question is, how do you decide which way to go, or what is the best possible? Right? So, yes, please.
If you specified it as a relative error rather than an absolute error, how do you divide? It would seem that you'd have to give the same relative error to both of your children unless you have an assumption about the magnitudes of the values that they're giving you.
So there are essentially two ways of looking at the error. So one is, as you said, the absolute error. Right? Essentially, the talk I'm giving today is actually based on the absolute error. But there's an equivalent notion of relative error as well. Essentially, where you actually specify, you can also specify the error in terms of relative to the absolute value. Right? And there's a separate piece of work on that, which I haven't covered, but essentially I can give you more details when we talk.
Okay, I'll think absolute error for the rest of the talk.
Okay, great. So now the policy question is, how do you do it optimally? Right? So remember, our goal is to do scalable monitoring. And our key constraint there is for scalability, we want to minimize the monitoring overhead. That essentially you want to minimize the number of updates flowing in the system. Right? So ideally, you want to set these filters such that you cull maximum updates as possible, not just at the least, but at the internal nodes as well. Right? So throughout, you want to minimize the total number of updates in the system. So if your input distribution, the input workload is uniform, then you might want to set these fits uniformly across all nodes in the system. Okay. But however, if your input is skewed, so for example, if your right subtree is generating a lot more updates than the left tree, you might want to give larger widths to the right tree and take away from the left. Right? And even within the same tree, sometimes you may want to give larger widths to the leaf nodes and smaller to the internal nodes, and sometimes larger to the internal nodes and smaller to the leaf nodes. Right? So what's the right thing to do here? And these are very quickly dynamic situations that are present in real-world applications. Right? Our goal here is to do self-tuning of these filter widths.
Why would you retain budget at any of the internal nodes rather than at the leaves? Is it just so you can more quickly distribute it, or right? Because they're not generating data, so is that the answer?
No, actually, but it's a very good question. So A very simple example where you actually want to give larger widths to the internal nodes is, for example, so think of it as you're getting consecutive updates. So you get an update with value v, and the next update you get is a value, say v plus 100. Okay, so this is value. You get a value v, you get value v plus 100, or so you say v1 plus 100, and you get v2 and v2 minus 100. Right. So I'm essentially computing, say, a sum aggregate. Right. So if I give, say, this filter width as unit 1, then there's no way I can filter that update, right? Because the next value is deviate from the previous value by 100 units. Does it make sense? So essentially, okay. So the higher level answer is that when you combine these updates, they can cancel each other out.
Sure, but they can cancel each other out whether you push the value or you push the budget down or not. Right?
Not quite, right? Because so in one case, essentially, I can give larger widths, larger budgets here, but still the value itself may still deviate. So think of it as v, the first value being v, the next value being v plus a million.
Okay.
Right? And similarly, essentially, so one thing goes up by a large amount, the other thing comes back by a small amount. And think of it as across the children.
And some of them stays within the range.
Or the aggregate value, in more general, the aggregate value stays in some, has very small change. So you can essentially, cancel that very small change by having a larger filter width at the internal nodes.
So first you get the leaves, but the law of large numbers gives you small numbers.
Small, essentially.
I have the same question as Bill. I similarly don't understand why you wouldn't spend the budget on the leaves.
Because if it's bursty at the leaves, then the budget, you don't have enough budget to get away with.
But it's not one budget. It's that if you don't spend it at the leaves, it doesn't give you more in the internal node, as far as I understand.
As far as I can tell.
You don't get more at the internal node for not spending it at the leaves.
No, you're not getting, because the total budget is fixed here, right?
Right.
Essentially, you're taking this budget from the leaf nodes and then putting it here. So the idea there is, suppose if I don't keep anything at the internal nodes and push everything onto the leaves, then the cost of the system is strictly, if I put in this, is at most the same cost, essentially, if you push all the budget to the leaves. Does that make sense?
The thing that you guys are disagreeing about is that you're saying if an internal node has a certain amount of budget and it gives some to the leaves, it loses that budget. And John is saying...
I don't understand why. I'm saying I don't understand why.
Right, you have to report, if you're an internal node, you have some idea of your values, right? And in particular, you know that your children are all within the ranges that you've assigned.
Yes, those are the guarantees.
Network update assumption, right? So when I get an update from a leaf that says it's moved out of its range,
right?
Then I know. Yeah, okay, I see what you're doing.
So essentially, then you are also propagating these updates up as well. So we good? Is John?
I'm still confused. I'm still confused about why there's a trade-off in budget between the parent and the child.
So the trade-off essentially is the following. Suppose I can keep, say, consider extreme cases. I can keep the entire budget here and give nothing to the leaves.
I don't understand why it's a trade-off. Why you can't. If I have the range 0 to 10, and I give 0 to 5 to one child and 5 to 10 to another child, right? Then I still have 0 to 10.
Because imagine.
So the trade-off essentially is in the term of that. Essentially, I'm trying to minimize the updates, right? So what you're really saying is by setting this width in such a way, right? The messages essentially you're getting, right? So if I get a message from my children, do I actually, when I combine them, when I aggregate them, do I still need to propagate it to my parent itself as well?
Right.
Right. So now the point there essentially being that sometimes you may not want to give very small amount of this budget to the children, but essentially keep your error window actually larger.
I understand keeping my error window larger. Why does that ever mean it is good to give less to my children?
Okay, so actually, since I want to, 58. So let me give you a very quick answer to that. So I'm going to for shortest time, I'm going to very quick explain the example, right? So here I'm essentially set this filter width as 4, 6, the other is 3, 4, right? My total budget is 5, the parent has 2, this is 2, this is 1, right? I'm computing a simple sum aggregate, which essentially take the sum is sum of the lows, sum of the highs, and then I apply my local filtering here, right? The local filtering essentially, I'm expanding this range by delta by 2 on both sides. So this is 7 and 10. And my delta by 2 is 1, essentially, so I'm expanding it as 6 and 11. Makes perfect sense?
Yep.
right? So now I get a new update value which has with value 6, and for that is value 5.
Yes.
Right? So now I don't need to do anything here because it already lies within my range.
Great.
Right? So you simply filter it out.
Great.
You need to send it up.
Yep. Yep.
Right? So you send it up here and you recompute, essentially reaggregate, right?
Yes.
You're already using the cached value from here and you use the updated value from the right trail. Right? Now your value is 8 and 11.
Yep.
So 8 and 11 already lies in the previous range, which is 6 and 11 that I reported to my parent. Mm-hmm. Right? So now essentially, because of keeping the budget here, right, I'm able to call that update. If I kept no budget here, then every time a leaf changes, I have to update it to my parent. Yes, precisely.
The budget's not on values, it's on error. So if the guy, you can't spend the margin of error twice, otherwise the margin of error is now twice as big as you originally expected.
Okay, I mean, if you
So it's that I didn't know whether to give that budget to the left node or to the right node.
or keep itself. It's I'm showing you a binary tree, but it's actually a 16 or 8
By
tree.
keeping it myself, go ahead.
The trade-off is if you keep it yourself,
Yeah.
then there's a decent chance that you can cull the thing before it goes all the way up to the root. You push everything down to the leaves, and anytime anything ever exceeds its budgeted leaf,
I agree.
it has to
I agree.
propagate all the way up
I
to the
agree.
root, and it's at a log n cost.
Okay.
Okay.
That makes sense.
So
Okay.
if you still have concerns, we're going to meet, so I'm going to.
Sounds good.
Okay.
Sounds good.
Interesting optimization problem to solve too.
Okay, so I'm going to skip that. Right. Sorry. So now it's not, well, I guess the problem is actually not just the optimization, but actually it's even harder because in order to adjust these widths, we have to send messages, right? So essentially you want to, not just want to minimize the number of messages that are being propagated due to the monitoring overhead, but essentially if you want to adjust these widths optimally, we also end up paying the costs of sending messages to adjust them.
So your optimality metric is total number of messages.
Total number of messages, both the going up as well as going down.
It's a popular metric.
Okay, so now to address these challenges, we have designed and implemented both a principled self-tuning and a near optimal solution. Okay, now note that you cannot apply heuristics here because heuristics may work for one workload but may not work for the other workload. So what essentially we need is a principled solution that uses the workload properties itself to guide the optimal setting of these filter widths. Right? Further, we need a self-tuning solution to adapt to dynamic workloads because workloads can change dynamically with time, and to make sure that the benefits we get by sending these messages exceed the costs of sending them. Right? So you want to make sure your benefits always exceed your costs. Right? And finally, we have done theoretical analysis of this problem and shown that our solution is the optimum online algorithm. Okay? So first I'm going to show you a workload-aware solution to estimate the optimal filter widths. So for any given workload, the key thing to consider is the variability or the noise in the workload. Right? Essentially, if you have a very high noise in the workload, then you need larger filter widths to cull its updates. Right? At the same point we were talking about, if you have value v and the next value is v plus million. Right? So if you have more noise in the workload, you need larger filter widths to cull its updates. Right? So I'm expressing this notion in this graph where the monitoring load on the y-axis is expressed in terms of our total budget delta. That is the error we are willing to tolerate, and the standard deviation or the variance in the input workload. Okay? So when you look at the left of this graph, when your error budget delta is much smaller compared to the noise in the workload, then you expect to filter very few updates because most of them will actually lie outside our range. However, on the right, when an error budget delta is much larger than the noise in the workload. So think of as a Gaussian, right? So for a Gaussian, if you have delta as say plus minus 3 times the standard deviation, you can filter out roughly 99% of its updates, right? So now you expect the load to decrease quickly until a point where majority of these updates get filtered. Okay? We capture this curve mathematically using Chebyshev's inequality, which allows us to express the expected message cost outgoing from any such filter in terms of the variance and the update rate of the input workload, as well as our input error tolerance delta. And the whole idea of doing this mathematical modeling is to estimate the optimal filter widths that we are setting at each node in an aggregation tree. No, actually, so there is none. That's why essentially we're using the Chebyshev's inequality, which doesn't make any input or any a priori assumption about the input distribution. Right.
Well, that's why it also doesn't quickly decay to 99.9%, right? It's that if you set, like he said, delta equal to 3 sigma, it's only 1/9.
Yeah. So yeah, so there is essentially, so this is not a very tight bound, but essentially this doesn't make any assumption about the input workload. Okay, so using this model, we formulate an optimization problem for a one-level tree where we want to minimize the number of messages being sent from the children to the root such that our total budget delta t is fixed, right? So your input error tolerance is fixed. So given that constraint, you want to minimize the number of messages being sent from the children to the root. Okay. So now solving this optimization problem, we essentially get a nice closed form solution. Now I don't expect you to understand this equation, but one thing I want to point out here is the optimal setting of these filter widths depend directly on the variability in the workload. That is both the variance as well as the update rates. And we extend this approach to a general aggregation hierarchy. Right? However, again, as I said, computing this optimal is not enough because we need to send messages to adjust these filters. Right? Yes, please.
Update rate doesn't seem very well defined to me.
So update rate is the number of say data, number of, for example, in a network monitoring application, the number of packets you're receiving per unit amount of time.
I understand that these are discrete systems, but I mean, it seems sort of abstractly that's continuously, that function, the value function is varying continuously, right? The update rates come almost as quickly as you're willing to look at them. In general,
right, so essentially you're describing some sort of a time windows at which actually you're looking at how these things are changing. So for example,
I mean, the update rate is something you choose, not something the system chooses.
No. So, well, we're essentially defining the update rate over a time window, right? So essentially you can look at it as somewhat of a burst. So essentially, so these are time windows. Essentially, you choose the number of updates you have received in a given time window, and you divide by the unit of time. Right? Does that make sense?
No, because the thing you're measuring over that time window is there's some underlying, let's call it a continuous function, that's updating infinitely often, right?
Yes. So essentially, so this is an approximation of how the continuous signal is actually being discretized. So essentially, as
I guess what I'm trying to intuitively it seems the standard deviation is well defined for any reasonable thing you're measuring, but the update rate is something you chose, right? You said I would like to measure these every tenth of a second. I'd like to. I mean, the update rate is an arbitrary value, and if the function is varying, if the value function is varying, it's not constant, then it will update at every window.
So what's really happening, right? So what's really happening is that when you essentially receive a data packet, right? Essentially, you're computing both the standard deviation. So this is being computed in an online manner. Essentially, you're keeping track of the update rate as well. So essentially, so think of it as in 1 hour, essentially, I'm keeping track of what all updates I'm getting, essentially how many times this value is being refreshed, right? So I'm not actually picking, I'm just picking the time window over which I'm looking at the system. I'm not actually picking how, because this is part of the input workload, how the inputs data is being generated, right? So okay. So as I said, essentially computing this optimal is not enough. We need to send messages to adjust them. So imagine we do this periodically. So say every 5 minutes, we go and we compute the optimal settings of these filter widths, and we send messages to adjust them. Now, as you increase the frequency of distribution, that is, you go from, say, 5 minutes to a minute to 30 seconds and so on, you're essentially getting more and more closer to the optimal. That whenever there's a difference between the current setting and the optimal setting, I'm going to send messages to fix it. Right? So essentially, you're essentially getting more and more closer to the optimal, and your filtering becomes more effective. Right? However, there is a point of diminishing returns after which the benefits you get are very marginal. Essentially, you keep sending these messages to fix the imbalance between the current setting and the optimal setting. The benefits you get are very marginal compared to the costs of sending these messages. Right? So in general, there is this trade-off between the message overhead and the frequency of budget distribution. So read this x-axis here as going from 5 minutes to a minute to 30 seconds, 10 seconds, and so on. right? So as we go from left to right, we are increasing the frequency of budget distribution, that we are sending messages much more frequently, right? So essentially then our total monitoring load shown in blue decreases, right? Because our filtering becomes more effective. However, there is a point of this diminishing returns after which this redistribution cost shown in red starts to dominate, right? Is the point coming across? So essentially our idea here is to make sure that the benefits we get by redistributing always exceed the costs of redistribution.
So there's an assumption here though, that you're doing a global redistribution as opposed to, say, just redistributing. Well, I guess, is this is the one parenting and
No, this is happening in general hierarchy.
I know you've got the recursive aggregating system.
Yes.
So, unless I'm incorrect, the way you're describing this, it sounds like there's an assumption that you're globally redistributing the whole tree. And one can imagine at least systems where you only redistribute subnodes that are the most out of whack, which would reduce the redistribution cost and possibly move the blue curve down.
Right. So essentially, which is precisely the point that when do you redistribute, right? So when I computed the optimal, I said by how much you redistribute, right? What is the optimal setting, right? So then this logical question is when do you redistribute? So ideally, essentially, you essentially want to move the global error distribution or the global budget distribution of the entire tree same as the optimal.
Right. But what I'm saying is that I think that's an assumption you're making that's not necessarily that at least requires an explanation of why it's a valid assumption. Because you could imagine, say you had a big tree, that's a binary tree, and the left half turns out to have its internal stuff completely out of whack, and the right half is pretty close to right. So you could reduce your redistribution cost by half by just just leaving the right half the way it is. Now you're not optimal, but you've cut down on the red cost substantially while bringing the black cost, getting most of the advantage of the black cost. Does that make sense?
So exactly. That's precisely the point. That essentially, how do you make that decision?
Okay.
Right.
So you're talking about
Yes, precisely. That's precisely the point, right? So essentially, what we're really doing is applying this cost-benefit throttling, as which you rightly said that if you don't really need to redistribute, then don't, right? So essentially, how do you make that decision?
But I'm making a different question. There's two questions, right? One is, are you far enough off optimal that you just don't want to redistribute at all? But the second question is, it may make sense to do a partial redistribution, and it sounded at least, and it still kind of sounds like you're making an assumption that you either redistribute completely or not at all.
So right, so the way the redistribution is happening is that at each internal node, which is the parent of its underlying children, is essentially making this decision that whether I need to redistribute it amongst my children and so on. And every internal node is doing that, right? So there is no notion of a globally, right? Exactly. So right, so essentially what we are really doing is we're applying this very simple key idea of cost-benefit throttling. It's not even recursive. Actually, so everything is happening. So each parent is actually the individual, So think of it as each internal node is the parent of its underlying immediate children, right? So essentially each of them is making this decision that from my subtree I want to minimize the number of updates that are happening, right? So here essentially we redistribute the budgets only when either there is a large load imbalance, that means there is a big difference between the current setting and the optimal setting, or the load imbalance itself is small, but over time it has accumulated. So it becomes a long-lasting imbalance. Right? So essentially, we redistribute to make sure then our benefits always exceed our costs. And we have done theoretical analysis of our solution and shown that our solution actually matches the optimum online solution. And for this problem, there is no constant comparative algorithm that exists. Yes, please.
When you described how to choose the distribution of error budgets between apparent children, from what I can tell, it didn't take into account any difference that would make in the later cost of redistribution.
Right. So
it felt like it assumed a static workload and said, if I never have to redistribute, this is now the correct thing. And now I feel like you're saying, well, now I'm going to make redistributions, but I'm not going to make those redistributions taking into account my possible desire to make future redistributions cheaper. And redistribution seems like actually a very strong argument for keeping error budgeted parent nodes.
Right. So essentially, it's right. So when you're essentially computing the optimal, you're looking at the distribution. Essentially, it has behaved over this time. Like essentially, like so. Yeah. So essentially, it's some notion of that the workload is going to look like this, or essentially it has looked like that. Right. So I'm computing the optimal based on that. Right. Essentially, and then exactly as you said, this essentially is taking out the dynamic aspects. That essentially, how do you make sure that your benefits are always, so when you redistribute, your benefits are always going to be better than the costs.
But couldn't you do better by also taking the cost of future redistributions into account when you assign?
Right, but essentially then you have to build more of a predictive model, right? Essentially how the distribution is going to behave, right? So the idea here essentially is we are building a general framework that essentially no matter what your distribution does, the system is still applicable in all cases, right? So
Tons of competitive algorithms do, where you kind of keep going until the cost of fixing it is equal to what you've already paid.
Yeah,
right?
I
And a
agree.
lot of them are doing it. Just like
okay, to see if this is effective, I'm going to first show you some quick simulation results, and then I'm going to show you results from a prototype implementation. So in this experiment, essentially we are using a 90-10 synthetic workload where 90% of the sources have zero noise. That essentially they're giving the same input value over and over again, and 10% of the nodes have very high noise. They're kind of the heavy hitters, right? So you expect your optimal algorithm to take all the budgets from these zero noise sources and give it to these noisy 10%. Right? So in this graph, I'm showing you the normalized message overhead on the y-axis, and on the x-axis, I'm showing you the ratio of our budget delta to the standard deviation. So think of it as, again, if you have delta as plus minus 3 times the standard deviation, you can filter 99% of the input updates. Right? And again here, lower numbers means better. Right? So first of all, compared to uniform allocation, which gives equal uniform filter widths to all the nodes, we reduce overhead by an order of magnitude. And compared to adaptive filters, which is the state of the art in this area, we reduce overhead by an order of magnitude and even beyond. Because what adaptive filters does is it periodically redistributes these budgets and hence wastes messages on useless adjustments. Whereas in our case, we only redistribute if benefits outweigh costs. Okay. To see if self-tuning approximates ideal, we use a uniform noise workload. That means all the data. I'm sorry?
uniform is better than adaptive.
Because it didn't send any overhead.
Because the
The adaptive blew a bunch of budget on redistribution that it didn't.
They didn't need. It actually blew more budget than it got, even though it was living in a world that was very unbalanced.
right. And actually, and I'm going to show you that the real workloads are actually very, very skewed. Okay. So, and for uniform noise workload, the optimal policy is to give these filter widths uniform, right? So again, our solution, self-tuning closely approximates the uniform. We are sometimes slightly better, and we have sometimes slightly worse, because the uniform allocation is the best online policy. It is not necessarily the optimum online solution, right? And again, compared to adaptive filters, we reduce overhead by several orders of magnitude. Okay. So I'm going to quickly show you some results from a prototype implementation. So I've implemented a prototype of PRISM on top of the SDM's aggregation system, and we use free pastry as the underlying DHT. And for this particular evaluation, I'm going to perform a distributed denial of service query that find out the top 100 destination IPs receiving the highest aggregate traffic from all nodes in the system. And the input workload here is taken from abelian traces. So before I show you the results, let me quickly give you a quick overview of the input data distribution. So to process this workload, we need to handle about 80,000 flows or attributes that send roughly 25 million updates in an hour. Right? So a quick calculation would tell you that a centralized system needs to process about 7,000 updates per second. So both in terms of bandwidth and processing. And further, this distribution is heavy-tailed. So if you look at the bytes distribution, then 60% of the flows send less than a kilobyte of traffic. And 99% of these flows send less than 400 kilobytes of traffic. However, this distribution is a heavy tail, and the maximum flow sends more than 200 megabytes of traffic. And you see similar patterns in the packet size distribution. Right? So now the key challenge here is, for doing self-tuning of these budgets, we need to manage or self-tune budgets for these tens of thousands to millions of these attributes. Right? So now tying it back to our running example, when you have 99% of these flows send less than, say, half a megabyte of traffic, and if you take, say, our say error budget, so even say 1% or 0.1% of the maximum flow, then we can filter more than 99% of these small noises, right? So essentially what I'm call as the mice flows, which send very few updates, compared to the elephant flows, which are really large, and which is the actual flows we are really interested in, the top 100 heavy hitters. Yes, please.
Did you compute the maximum flow?
Right. So there are several techniques. So you can actually start the system by essentially computing an estimate, right? But the system allows you can actually update the error value as the system progresses. So essentially, as you're running, you can update, you can input new values at any point in time. So you can think of it both in terms of the absolute as well as the relative, right? So in relative statistics, you can always say within 1% of the maximum flow. In absolute statistics, you can take, say, 1% of, say, 100 megabits per second. And you compute the value and you say, well, it is something different, then you can re-input the value back to the system.
Right. So this actually brings us back to a question that I had earlier, which is, does it make sense to build aggregation trees over IP addresses as opposed to building an aggregation tree over the 800 hosts that you have, where each host sends up its 100 best things, and then it just, I mean, it doesn't give you the cool optimization problem, but as an engineering solution, it might actually work better.
Actually, my claim is the correctness actually gets hurt. And so correctness is violated given your solution because the top 100 actually might not be in the top 100 of each individual node, right? So each node, not necessarily, right? You can actually have small values at each of them, but when you aggregate them up, yeah. Right. So
IP address of your kid's school is different depending on the count.
So this graph shows the results. So compared to a centralized system that incurs a cost of, so these are the absolute numbers, about 7,000 messages per second. If you take an error budget as even 5% of the maximum flow, we can reduce this monitoring overhead by 3 orders of magnitude. And by using a key optimization, we get another order of magnitude improvement. So I'm not going to go into details of this optimization. The punchline here is by doing the self-tuning of these error budgets, we can reduce the monitoring overhead by several orders of magnitude, which is really important for scalability. So that's the key argument. Yes, please.
There's a ton of work on identifying the most popular anything, the most popular million URLs, or the most popular IP addresses. And, how does this compare to all those other?
Right, so again, see I guess the work essentially you mentioned, it's being popular in the databases, kind of networking communities as well. Essentially the idea has been, or most the common notion is essentially we're doing this common top 100 at each individual site, right? Essentially, and the idea essentially is to then aggregate it at a central point, essentially more of think of it as a one-level tree, right? So essentially, so this again in this system we are essentially assuming this is a completely distributed environment, where essentially the top 100 at each local site actually doesn't suffice, right?
I guess if I go to the Arbor network sites that we have here installed, I can do top 100 heavy hitters and just cross our network.
Okay, so I guess we can cover more details, but essentially the idea is that we're building this in a complete distributed environment. So the top 100 globally aggregate across all the nodes in the system. But I mean, if this published work, I'll be interested in. Okay, so I guess. Okay. So to summarize the contributions of AI, we have given you a flexible mechanism in which you can take a global budget and divide it in any manner across the nodes in the system. Right? We're giving you an adaptive algorithm that performs self-tuning of these budgets to minimize the monitoring overhead. Our solution has 2 key ideas. We are estimating the optimal based on the variability in the workload itself. And we only redistribute if benefits exceed the costs. Right? And our analysis shows that our solution is the optimum online algorithm. And using experiments, we can get significant reduction in the monitoring load by even using a very small AI. So AI of 1% and 5% actually gives you several orders of reduction in the monitoring overhead. Okay. Which is in fact the case for real workloads, which is really, yes. Because if you really think about it, if your distribution is really uniform, then we don't really need these sort of fancy optimizations, right? But real world workloads are in fact very highly skewed. Okay. So I'm going to very quickly actually touch the second dimension of precision, which is the temporal imprecision, right? And again here, I'm assuming that nodes in the network are reliable and links have small delays. And I'll describe how NI handles cases when these assumptions do not hold. So the key point essentially I want to make from this part of the talk is by combining AI and TI, we can get significant reduction in the monitoring load, which is really important for scalability. So using AI and TI, we have built this application which is currently running on Planet Lab on about 500 nodes, which detects the top 100 destination IPs that receive highest traffic from the Planet Lab nodes. Right? And this application is currently running on the Planet Lab infrastructure. So in this graph, essentially, I'm showing you the results from this application, where the y-axis shows the message overhead, and the x-axis shows the temporal or the TI budget. And these different lines show the different AI settings. And again here, lower numbers are better. Okay, so if you compare going from AI of 0 to AI of 1%, we get a reduction in monitoring overhead by a factor of 30. And you get another order of magnitude load reduction by going from AI of 1% to AI of 20%. Okay? So essentially, we're getting these orders of magnitude reduction in the monitoring overhead by using a small AI error tolerance. Similarly, by using TI, if you go from 15 seconds to 1660 seconds, you get roughly an order of magnitude reduction. Right? And note that for this application, having a TI of 60 seconds is reasonably good. And having an AI of 10% is reasonably good, because we are interested in the top heavy hitters list. Right? So by combining AI and TI, we are getting several orders of reduction in the monitoring overhead. Another advantage of combining AI and TI is we get highly responsive monitoring. So for example, for approximately the same cost as AI of 1% and TI of 5 minutes, we can give you 20 times more responsive monitoring at AI of 10% and TI of 15 seconds. So this AI and TI combination is really powerful, as it gives us several orders of reduction in the monitoring overhead, as well as gives highly responsive monitoring. Okay. So until now, I have talked about AI and TI, how they give us high scalability and how they give us strong accuracy guarantees. However, this is all nice and great in an ideal world, because in practice, failures can cause the system to violate these guarantees. Therefore, we define a new abstraction, network imprecision, that bounds uncertainty due to failures. Since this is a new abstraction, it'll take me a couple of slides to define it, but let me motivate why NI is important. NI is important for 3 reasons. First, it allows us to fulfill the guarantees of AI and TI. And in comparison, existing systems today only give you best effort. And I'm going to show you that best effort can be arbitrarily bad, or it can have very high error in practice. Second, in the presence of failures, AI and TI can actually increase your risk of error. Right? So therefore, NI characterizes how accurate the results really are. And finally, using NI, AI and TI can now assume that nodes in the network are reliable. Right? So their implementations get simplified. And NI handles cases when these assumptions do not hold. So the key motivation for NI is that failures can cause the system to violate AI and TI guarantees. So in this very simple example, we have a monitoring application that's returning a query result as 120 requests per second. And note that we're essentially using our aggregation trees to compute the global result. And here, the subtrees, the aggregate value of the subtrees are being cached at the parent, right? Because we're essentially doing this to minimize the cost, because if we don't get any update, then we guarantee that the subtrees values lie in that range, right? So given this AI and TI precision requirements, we're getting this answer, and we're doing caching of the subtree aggregate values, right? So now when you get this result in the presence of failures, what does it really mean? Does it mean that the load is between 110 or 130? Or in fact, the load is actually much higher. But in fact, there was a disruption which prevented this new update from reaching the root. However, for the root node, it's still using the cached value of the subtree, thereby reporting you an incorrect answer. Or in fact, the load could be much smaller. But there was a subtree that essentially moved to a new parent. So a reconfiguration caused this root to count the subtree's value twice. Essentially, it's caching the subtree's value here, as well as the aggregate value being provided by its right tree. Right? So here, reconfiguration causes double counting. Right? So earlier, we made the claim that we can give you strong accuracy guarantees without failures. but in practice, when failures happen, what guarantees can we really give? Right. To see how bad it is in practice, we built and deployed this application on Planet Lab, where we're keeping track of the per experiment global resource usage on all 800 Planet Lab machines. Right. On the y-axis here, I'm showing you the CDF of answers, and on the x-axis, I have the difference of the truth. So essentially, we are taking the difference of a reported value from the true value, and you get the true value by taking offline processing of the logs. Okay. So 2 things to note here are that half of your reports deviate by at least 30% from the true values, and about 20% of the 1/5 of the reports deviate by as much, roughly, about more than 70%. Right. So now when you get an answer, where does the answer really lie? Does it actually lie here, or here, or actually is even beyond? Right. So this best effort can be arbitrarily bad in practice. Right. So what's the solution? Do we just give up that we cannot give any accuracy guarantees in the presence of failures? You have an answer, you have a question?
I actually don't understand what the point of comparison was against what the best effort PRMON does.
So the notion of comparison essentially is we're taking the true value. This is the oracle value. So essentially we log everything, and when we get an answer, we essentially do offline processing of the logs to compute what the answer should have been versus what the system is telling us.
And the system, what is the system that you were saying?
This is our PRISM system, which is deployed on the Planet Lab.
Okay.
CDF wasn't actually a whole lot better than what you get if you guessed randomly, right?
I'm sorry?
CDF actually wasn't that much better. It was a little better, but it wasn't hugely better. So you get a uniform, you get a straight line if you guess randomly, right?
Yeah, you actually get a pretty heavy tell. Essentially, these answers can actually deviate by a lot.
Depends on whether they're relative errors or not.
Well, right, but you're reporting this as being 30%, 65%, so the relative errors, right, in this graph. So if I just made up
If you made up random numbers between 0 and 100, and the truth was always 1, you'd be off by more than 50%.
Well, this 100 obviously has a special meaning, right? Because it's a coincidence that it happens to arrive at 100, or what he's doing is he's putting the smaller number always on the denominator.
Right. So essentially this has been normalized, right? The larger of the denominator. Right.
So, I mean, what Bill's saying is if I make up a number between...
Yep.
Okay.
So what's the solution? So do we just give up that we cannot give any accuracy guarantees in the presence of failures? Sounds great, right? So the real thing to actually understand is that we have to accept that our systems are unreliable, and therefore we cannot guarantee to always give the right answer, right? So instead of always guaranteeing to give the right answer, our idea here is essentially to quantify the stability of the system when an answer is reported, right? So go back to our intuition of this stable good or bad flag, right? So when you get an answer, you get this good or bad stable bit. If the bit is set, the system is stable, and you can trust the accuracy of the reported answer. Otherwise, our AI and TI bounds may not hold, and you cannot trust the accuracy of your answer, right? So it'll be great if I can always give you this green light that yes, you can please trust this answer, versus a red light that no, you cannot trust the answer, right? However, in reality, large-scale systems are never really 100% stable.
It's a yellow light all the time.
Yes, precisely. Thank you. So large-scale systems are never really 100% stable. So we quantify how stable the system is when an answer is computed. Okay? And the way we essentially quantify system stability is using 3 simple metrics: NOL, nReachable, and nDupe. NOL is simply the number of live nodes in the system. Okay? nReachable gives you a bound on the number of nodes who are meeting TI guarantees. That means what part of your network is reachable. That means from what part of the network you are getting the recent updates from the nodes.
But how can you tell? You just put a lot of effort into not sending update. You put all this effort into never sending messages. And so it's theoretically impossible to differentiate between a broken network link and I suppressed the messages because you did such a great job of allocating the budget. So how can you tell?
I'm going to come back to the scalability aspects in just give me a couple of slides.
All right.
Yeah, but thanks.
I know you guys like the Socratic method of lecturing, but we've got like 15 minutes left,
Okay.
so maybe we'd get through his talk.
But thank you very much for all the enthusiastic questions. Thank you. So the 3 metrics we use essentially to quantify system stability are NOL, nReachable, and nDupe, right? As I said, NOL is the number of live nodes in the system. Unreachable gives you a bound on the number of nodes whose recent inputs are being used in the reported answer. And undupe gives you a bound on the number of nodes whose inputs may be doubly counted. Right? So these three metrics together characterize the accuracy of reported answer. So in this example on the left, when you have 99% of your network is reachable, that means the answer that you're getting reflects recent updates from 99% nodes in the system, and 0 inputs have been doubly counted. Then it is highly likely that the answer you get reflects the true state of the system. Right? Whereas if you compare it to the example on the right, when you have only 10% of the nodes that are reachable, and half of the inputs may be doubly counted. That means the system may be reporting you either a highly stale answer or essentially overcounting the inputs of the nodes. Right? Therefore, you cannot trust it. Right? So tying it to our earlier motivating examples, when a write subtree disconnected from the root, then our unreachable will indicate that only 40% of your network is reachable, right? Because a large chunk has been disconnected. And therefore, the answer you're getting may be highly stale because the parent may be caching the disconnected subtree's value. Right? Therefore, you cannot trust this highly stale answer. And similarly, when a subtree reconfigured or when a subtree joined a new parent, then even though all of your network is still reachable, that means I'm getting the recent updates from all my nodes, half of these inputs may be doubly counted. Therefore, the answer you're getting may essentially have the input contributions of nodes multiply counted. And therefore, the answer might be overcounted, and you shouldn't trust it. Right? So even though we cannot guarantee to always give the right answer, NI is still useful because it's now telling us how these disruptions are affecting the accuracy of the global result. Okay? And essentially, we use this metrics to characterize the state of Planet Lab. This is actually a couple of years old, but essentially the graph I generated for this OSD deadline actually doesn't look quite a whole lot different. So here what we actually see is that you get lots of disruptions in the Planet Lab nodes, even though you have actually very few physical failures. So out of 100 nodes, only about roughly 5% of them actually failed. But you actually get lots of disruptions, which supports our claim that real-world systems are never really 100% stable. They're always in the yellow light. Right? And therefore, these disruptions have a big impact on the accuracy of your answers. Right? So now we have seen that NI is useful to characterize the accuracy. Can we actually use it to improve this accuracy? So a simple technique that we use is NI-based filtering. This is a part of series of techniques, but I'm going to show you results from just one technique today. So in this NI-based filtering, we mark an answer's quality as good, marginal, or bad based on the number of unreachable and doubly counted inputs. Okay. So and for simplicity, I'm condensing my 3 NI metrics into a single number. Okay. So NI small means things are perfect, and NI large means things are imperfect, or there is too much churn in the system. And these different lines show the different NI thresholds. So if you compare the best effort system, where 80% of the reports can deviate by as much as 65%, by using this very simple technique, we can guarantee that 80% of reports have at most 15% error. Right? So a further benefit is that when we get an answer that's actually tagged with NI, I know if my answer lies in this range, or this range, or this range. Whereas compared to best effort, when I give you an answer, I say, well, the accuracy could be here, or could be here, or could be somewhere else. I don't know. Right? So by using this NI, I'm able to characterize both the accuracy as well as improve this accuracy. So now we see that NI is useful, but can we compute it efficiently? Right? So the good news is yes, these NI metrics are simple to implement as they're conceptually all count aggregates. Right? So NOL is the number of nodes in the system, and reachable is the number of nodes whose recent inputs are being used, and undupe is the number of nodes whose inputs may be doubly counted. However, they are difficult to implement efficiently. As you rightly pointed out, there's a big scalability challenge. In particular, the big challenge is that we need to compute NI for each aggregation tree in our system. And secondly, we need to perform active probing of each parent-child edge in each aggregation tree in the system. Okay? So the first challenge here is that we need to compute NI for each aggregation tree in the system. And the reason we need to do that is because a failure can have different effects on different trees. So for example, here, the failure of this node only disconnects a leaf from this aggregation tree. Right? However, in a different tree, the failure of the same node disconnects an entire subtree. Right? So since now a failure is affecting different trees differently, you need to quantify its impact individually for each aggregation tree. Right? And second, to give a TI guarantees. So these are the challenges to compute this NI matrix scalability. Right? The second challenge in computing this NI matrix scalability is we need to perform active probing of each parent-child edge in each aggregation tree. And we need to do that to satisfy our TI guarantees. And a naive way of doing incurs order n messages per node per second. And for a 1,000-node system, this requires about 100 messages per node per second. Okay. So what's the solution? To address these challenges, we're going to use a particular property of our DHT system and use a particular technique that a set of our forest of these DHT trees forms an approximate butterfly network. And in particular, I'm showing you this 16-node this butterfly network for a 16-node tree, 16-node system, and this butterfly network encodes all the aggregation trees in the system. So for example, an aggregation tree like this, and another aggregation tree like that. So for scalability, our key idea is to reuse common calculations across different trees. These common calculations are for computing the NI matrix. So in particular, each node in this butterfly network is the parent of two trees, an aggregation tree underlying it of children that compute an aggregate value, and an aggregation tree of parents above it that depend on this underlying tree as input. Right? So now the idea of scalability here is rather than recomputing the aggregate value of this blue tree separately for each parent in the red tree, I'm going to compute it only once, and then I'm going to forward that value to each parent in the red tree. And essentially, we do this for the entire DHT system, for the entire butterfly network in our DHT system. Right? And by doing this, we reduce the cost from order n to order log n messages per second. And for a 1,000-node system, this only requires about 5 messages per node per second. Okay. We verify this experimentally. So as you increase the number of nodes, the per tree cost grows linearly. This is on a log scale. Okay. Whereas using our dual tree approach, this cost grows logarithmically. And for a 1,000-node system, we reduce it from about 100 messages per node per second to only about roughly 5 messages per node per second. And this grows logarithmically. Okay. Yes, please.
I withdraw my question.
Okay. We also have one-on-one, so I can answer that. So, okay. So to summarize the contributions of NI addresses the fundamental challenge that failures can cause the system to violate our AI and TI guarantees. And since we cannot guarantee to always give the right answer, our key idea is to quantify the stability of the system when an answer is computed. Right? We generalize this notion of stability or the stable bit using NOL, nReachable, and nDupe metrics. And our system provides a scalable implementation of these metrics by reducing the cost from order n messages to only about order log n messages per node per second. And by using NI, we can improve the accuracy in our monitoring results by up to an order of magnitude for the workloads we considered. Okay. So in this talk, I've talked about a bunch of things. How we use AI and TI to achieve high scalability, and how we use NI to ensure correctness of results. So let me tie it to the bigger vision or the bigger picture of my work. Our key idea or our big goal is to do scalable monitoring. In order to do that, we face two big challenges: scalability to large systems and ensuring accuracy despite failures. To address these challenges, our key idea is to define precision as a new unified abstraction. This abstraction has good properties. It combines these known ideas of AI and TI in a sensible way, and it gives you big scalability benefits. And NI is a fundamentally new abstraction that enables AI and TI to be guarantees in practice and greatly simplifies their implementation. And a prototype provides a scalable implementation of these metrics. For AI, we provide a self-tuning near optimal solution to adjust these filter widths based on dynamic workloads. And for NI, by exploiting the symmetry of our dual tree butterfly network, we can reduce the implementation overhead by several orders of magnitude. Okay. Now, apart from PRISM, I've worked on several other projects and built other systems that I haven't covered in this talk, but I'll be happy to talk about any of them offline. With that, I conclude my talk, and happy to answer any questions.
Oh yeah, 3 minutes. Go ahead.
Yes, please.
So when you talk about NI, it seems like this. I have this value, but don't trust me because the system is unstable at the moment, right? But the thing is that the real interesting event that we want to monitor through this system may be correlated with that system instability. So all the important things is happening, especially at that time frame, then what's the value of this NI?
Right. So exactly, the aspect essentially being that when you're detecting in sort of anomalies in the system, essentially you are detecting that anomaly based on, say, so think of it as a query answer, right? Essentially, an anomaly is, there's been a lot of traffic from, say, node A to node B, which is not FTP traffic, but essentially the huge chunk of traffic, right? So essentially, the point being that how do you actually get the correct value or the accurate value of that, right? So essentially, one aspect of NI is to characterize when there is instability in the system, right? The other aspect, which I briefly touched, and I can actually give you a little more flavor very quickly, is the notion of how do you improve this accuracy, right? So one technique I talked about was you can actually do this NI-based filtering. Another very simple technique we use is consistency versus stability. Essentially here, we are using redundancy to actually improve the accuracy. And the idea here is simple, that when we are computing an aggregate result in an aggregation tree, instead of using one tree, we're going to use k such trees. And you're going to pick the best result. And our actually practice shows that, and there's also some theoretical analysis that if you use k very small, like k 4 or 5 trees, you can actually improve this accuracy by a lot. Right? So essentially what we're really doing is that we are taking, computing an aggregate value redundantly across multiple trees and picking the best result. Okay? And this actually graph shows the improvement that this is just using this redundant aggregation where you can improve this accuracy by 5x. And when you combine this multiple trees with filtering, you can actually improve this accuracy by 10x. Right. So essentially, yeah. So we are approaching the problem that you just mentioned by essentially trying to improve the accuracy as much as possible when there are reconfigurations, right? Because that's one plausible way to know that if there are any problems in the underlying system. Does that answer your question? Okay. Hey, yes, please.
So another way to cut the data rate would be to do statistical sampling of the. That's the normal. So do you throw that into?
Yeah. So essentially, it's. I think I want to make the claim that essentially sampling is actually kind of a plug and play in the system, because when you're getting an inputs from the underlying system, right? Essentially they already have some error. When you say sampling, it's 1 over m or 1 over square root m, depending on what sampling you use. So our error actually becomes additive in the sense that now you actually have error because of the sample data, and so on top of that we're introducing additional filtering. So for the system itself, it's completely transparent that actually, yes, your input distribution, rather than keeping track of each and every update, you keep track of sample data. Right, essentially, so when I'm updating these statistics, these are actually based on the sample statistics. Yes, please.
An interesting question that you might be worth exploring is if you do system-wide sampling and then send the samples to a central location or something like that. Are there competitive approaches from an engineering standpoint that don't have the complexity of the trees that still end up? In other words, it seems like there's a straightforward,
yes,
strong answer.
Yeah, actually, so that's a good point. That yes, you actually. So think of it as very bare bones approach that you essentially sample, say, every few often, and then say periodically every 5 minutes or so, you go to the central site and then sync everything up and correlate. Yes, so that is plausible. The argument there being essentially that now I want to do monitoring not at 5 minutes, but at scale of 5 seconds. Right.
Well, I guess what I meant is, it seems like if in most examples you're looking for, the largest event, then you can just keep making the sampling sparser and sparser. And if the event is big, it's always going to stick out the samples.
So but essentially you're also paying the overhead, right? So essentially for the DDoS query that I mentioned, right, I'm essentially detecting it. The system right now actually detects it within 15 seconds. So if there is a flow that actually becomes very large over a window of 15 seconds, then essentially the system detects it very quickly. Whereas essentially for something which is more of a periodic logging at a centralized site, essentially now have to do this all the time, right? So even though my local events may be important, may not be important, I have to send them anyways, and essentially, send them much more frequently as the time calendar you're looking at, right? So there's a big scalability issue in that.
Okay. I think we all should thank our speaker.
Thank you.